Okay, why don't we get started? So it gives me great pleasure to introduce Shuo Yang from DJI. And for those of you who are somehow or the other not aware of the drone world, I should point out that DJI has become, in the last few years, a kind of real force to be reckoned with. They have become the dominant force in consumer drones. You know, if you're looking for something $200 and above, there's definitely a DJI drone that you can buy. And you know, we have been watching the people working in air vehicles have been watching the evolution of these drones with some incredulity, trying to understand how they're doing this. They've been introducing not only these great consumer products, but they now have this new line of industrial products, which are fabulous machines. They're built beautifully. They're easy to use, and we're now able to use them as platforms to do some of our autonomous stuff. And then they're further chasing us because they're introducing some of this autonomy themselves to do this. So you know, it's great to acknowledge success, phenomenal success. A company that's sort of come from very small company to becoming sort of the dominant player in this industry, beat out all kinds of other players in this industry. So today we're fortunate to have Shuo here to talk to us about some of their products and talk about a competition that DJI has been sponsoring called the RoboMasters program. Just a little bit about Shuo. He got his degrees at Hong Kong University of Science and Technology, his bachelor's and master's, and since then he's been working on the flight control and navigation for a very wide range of products that DJI puts together. So we're very fortunate to have him here. He's going to give us an idea of what they have been doing and hopefully a little bit about the future.
Okay.
Welcome.
Okay. Thanks, Sanjay, for introducing me. Good afternoon, everyone. As Sanjay just introduced, I'm the technical director at DJI. I was responsible for a few products at DJI, and when I came to Carnegie Mellon, I saw a few students and projects has been using our drones for your research. I'm glad we helped you. And these days, been talking to those brilliant students and the faculties, and I think people would agree that the Robotics Institute has the greatest people and the projects in the world. And I'm very excited to come here to share with you some thoughts on drones and robots in general from DJI. Today, my talk has a title, From Drones to Robots, the road to make technologies more accessible. In this talk, I'm trying to include topics from different areas for different engineers and researchers from different backgrounds. I won't go deep into details, but I'm happy to talk to you in private after the talk and during the reception. Well, let's get started. As a consumer product company, the most direct way to make technology more accessible to normal users is to make cheap, affordable, but integrates as many technology as possible products for users. And this will be the first part of my talk today. I'm going to review some technologies we have developed on our products. And for the second part of my talk, as Sanjay just mentioned, we are going to introduce a robotics competition we have been supporting for years. It's a indirect way to make technologies more accessible, but I would say it's more enjoyable and meaningful to work on, and that will be the second topic of my talk. Oh, probably I mute sound here. This is a video we released by the end of year 2015. The video is called the Phantom X concept. In this video, we illustrate some ideas that we think a future drone would have. In this video, a drone called Phantom X is introduced. The drone is able to be slowed to start immediately, and the drone is able to track a person and follow it, and able to avoid obstacles on its course. And multiple drones can work together to get different angles of views of a certain person. This video actually is an idea that we want to show what we think of the future of aerial imaging. We think that we should let users to focus on content instead of manually operate the system. We want drone be able to fly anywhere, even in those dense natural environment, and even beyond visual distance. Finally, we think a drone is very important for a drone to be able to control without a remote controller, but interact with users using the most natural ways, such as the gestures. Well, at this point, actually, we are not making a flying camera. We are rather making flying robots. And DJI, as always, we think ourselves as a robotics company. And Phantom X is not merely a concept. It's a milestone on a roadmap, and we are working on this road steadily. So in the following year, 2006, we released 4 products that integrate computer vision and other sensoring technologies that enables them to be able to perform autonomous flights by themselves. These products are Phantom 4 and Phantom 4 Pro, Mavic Pro, and Inspire 2. They come in different sizes and shapes, and their price are different, and their target user are different. For example, the Mavic is really small and it's foldable, so it's convenient for people to travel and for people who do outdoor sports to carry it. Inspire 2, on the other hand, is a very large and expensive drone with very professional cameras and other functionalities. Those are for people who want to have a high quality video shots. The core components of all these systems is called flight autonomy. It's a component that enables drones to be able to visually positioning itself in GPS-denied environment, and is able to do object tracking and obstacle sensing. And we built some intelligent flight modes on this component. If we see it from an academic way, then these functions corresponds to some technologies such as visual odometry, multi-sensor fusion, depth perception, and also deep learning-based object tracking and detection. I will introduce these functionalities in the following slides. The first fundamental thing is we build a specialized hardware that contains a bunch of sensors, including multiple IMUs, barometers, magnetometers, and a lot of cameras. And we have a heterogeneous computing platform. Consists of microcontrollers, special vision processing unit, image signal processors, and also application processors. In total, there are 24 computing cores on this hardware platform. And we're able to process all the sensor data simultaneously and fully on board. Oops. The first technology we implement on this platform is multi-camera and visual inertial combined visual odometry. We process image streams from 6 or even more cameras, and this image stream will be processed by the hardware, and the result is fused with GPS, sonar, and other sensors to get a full state estimation of the entire system. The most important part is stereo vision. Actually, the 4 cameras on the system forms 2 pairs of stereo visions. One pair is downward facing, and another pair is forward facing. On Phantom 4 Pro, actually, we have a backward facing stereo vision. So in total, we have 3 pairs of stereo visions. And as some of you may know, actually working with stereo vision cameras is troublesome sometimes because the relative position of 2 cameras is critical for your algorithm to perform precisely. When we do research, we know we can always do extrinsic calibrations using a chest ball. But for our product users, people who don't know computer vision, they don't know how to do extrinsic calibrations. So we have to devise a self-calibration algorithms that's always running online to let cameras to able to detect the change of extrinsic parameters and adjust the parameters online so that our users don't need to calibrate the sensors by themselves. Also, we have to be careful when the algorithm running in different environments. For example, if the drone is moving on a flat surface, then we can do optical flow to do velocity estimation. But if the surface is uneven, then some of the assumption of optical flow algorithm is invalid. In this case, we have to identify a plane, and also we may need to change algorithms to keep it robust in those environments. The videos on these slides demonstrate how our system can work smoothly in an indoor GPS-denied environment. Even the system is being touched or dragged away, it's still be able to return to its position. Another technology we implement on this system is depth perception, and we have a different set of sensors to achieve different level of depth perception. Using stereo vision cameras, we can estimate depths up to 30 meters. And we also create another type of flight sensors that's being mounted on the side of Phantom 4 Pro that can detect distance to up to 5 meters. Also, the main camera used by users to take videos or photos can be used as a monocular sensor to achieve depth estimation for up to 200 meters. With a good visual odometer and depth estimation, actually we can realize some intuitive flight modes based on these technologies. The first functions is tap fly. Actually, it's quite intuitive. On the monitoring screen of the drone, users only need to tap a direction, and this direction will be projected back into the real world, and the drone will start to do a ray tracing function. And when it's moving towards that direction, the drone is able to avoid obstacles on its course. This function has a fancy version called draw, where users not only point the direction, but also draw a trajectory on the screen. And the trajectory will also be projected into the real world and being automatically smoothed, and the drone is able to use this smooth trajectory to fly a curved trajectory. Also, this function can be combined with intelligent homing, where the drone, when the drone is far from the starting point, is able to generate a trajectory and return to the home safely. The next important piece is deep learning. Actually, primarily, we developed an algorithm called active track. This tracking function is robust compared with some baseline methods such as compressed tracking and TLD. Our algorithm have a number of advantages. For example, it can deal with human body deformation better than baseline methods. We also have some engineering tricks to do failure recovery and handle occlusion properly. Also, more importantly, the algorithm is carefully optimized to enable it to run on embedded systems. As you can see in the below video, even the car is moving under clouds, the algorithm is able to track it steadily. We also continue to add more classifiers to the system using more deep learning techniques, where we can achieve that kind of natural interaction between drone and the user. Basically, we have a classifier to detect whether the user is waving hands or making some special gestures so that the drone will react. For example, take a photo and or start tracking a person. And by this deep learning algorithms, we can let users to interact with drones with new methods. Deep learning actually can also give us insights on how can we execute low-level control for a drone. For example, if the object to be tracked is a car, we can know that if the deep learning classifier tell us the object to be tracked is a car, then we can know that first, this object is not likely to deform. Second, this object may move very fast, but a car, the trajectory of car is most of the time is smooth and continuous, and the car won't have rapid turns. Then our control algorithm can be aggressive. On the other hand, if the object to be tracked is a human body, then we know that this object is likely to deform. And human can run and stop immediately and take a rapid turn. So its movement is more unpredictable. Therefore, the control algorithm has to be conservative in these scenarios. A better example would be also an interesting corner case would be consider the case where a person stands still and this person crouched down. Then our deep learning algorithms will have a bounding box around the person. If the person crouched down, then the bounding box will shrink. At the same time, if the person suddenly runs to a far place, then the bounding box also shrinks. Actually, for a monocular-based deep learning algorithm, we cannot tell whether the person is crouched down or moved to a far place. If our controller is aggressive and when the person crouched down, then the drone starts to accelerate, that can be very dangerous. Therefore, the controller has to be conservative when tracking a person and is able to use other techniques to distinguish whether a person is really moving fast or crouched down, have deformation. In conclusion, I show a video demonstrates what's happening in the back end when the drone is tracking a person. In the video here, the map is constructed from the depth information drone gathered using its depth perception algorithms. And the trajectory of the drone is estimated by visual odometry and GPS. The target position is detected by a GPS classifier. And our algorithm is able to plan the trajectory in this mapping environment and predict the next possible location of the target and decide a target position, a target direction for the drone. When this system is running, it's doing drone state estimation, target state estimation, online 3D mapping, and trajectory planning, then also feedback control. So a bunch of planning, control, perception algorithms is running together to achieve an effect like this. So with all these technologies, we are able to achieve the results we have now. These are video clips we gathered from YouTube randomly. Our users create astonishing videos using Phantoms or Inspire or other DJI products. They are able to create some interesting shots that even beyond the imagination of some best film directors. And these shots are hardly possible before, and now it's able to be realized using a single drone. So people may ask, well, what's your next step? What's your future plan? Actually, we are proud of our current work, but we always want to do more. We think that for aerial imaging, actually, we are still far from Phantom X because there are a number of technologies we still haven't got there. For example, multiple drones collaborate with each other. That's quite difficult to do because you have also to deal with communications between the drones and the delays happen between them. Also, gesture control, although it's very natural, but there are some problems you have to solve in order to let drones to precisely follow the gestures and prevent some failure cases. Beyond aerial imaging, there are more possibilities. For example, industrial applications, as Sanjay just mentioned, and we're also happy to see that a number of labs in here at CMU are using our products for your applications. Also, we want to enter general robotics applications, but as I said, the purpose of DJI for making products is we want to make technology more accessible to its users. So no matter what applications we develop, we think this is a core value that we should focus on. So this belief inspired us to create a new types of robotics application. So before I introduce the application, I would like to share some thoughts we have on robots in general. Now, people are well known that robots actually have a general framework when it's working in an environment. Basically, we build a robot, and this robot must interact with its environment. The robot generates actions by its accelerators. That can be a locomotion or an interaction with objects in the environment. And the robots gather information from the environment by its sensors, and we call sensors as observations. So for any robotics applications, actually, we have to think two questions. First, what the environment this robot would work with? And the second, how complex this robot should be. So there should be a metric to evaluate the difficulty of robotics applications. Well, from my point of view, I would rather use the following metrics. First, for the environment, actually we can estimate how unstructured this environment can be by a quantitative spectrum. The world we live in is completely unstructured. We have rainforests and waters. These are hard to model. And by modern civilizations, we are able to convert some of the unstructured environment into structured ones, such as highways and cities, buildings. Inside the buildings, inside those completely artificial objects, we're able to make some fully controlled, fully structured environment where we can do experiments. Also, we are able to do a digitized virtual environment where we can have the position, orientation, size of any objects. In this simulated environment, everything is structured. So that's a spectrum to measure how representable or how unstructured an environment can be. We have another spectrum to model to measure the complexity of robots. Humanoid robots, obviously, it's the most complicated and difficult robots. There are other humanoid robots for simple applications, for example, football, soccer. DJI drones, it's also some robots, but with also simpler configurations. I would point out that actually a robot that built in lab is always more complex than robots that being already in mass production, because in manufacturing industry, we have different ways to reduce the complexity of robots. There are also extremely simple robots, for example, Lego robots for kids to study robotics. If we combine the spectrum together, we actually get a coordinated system. Intuitively help us to evaluate the complexity and also the difficulty a robotics application can be. On this coordinate system, the third quadrant are those simple and easy to make robots. On the first quadrant, those are very complicated, very high-tech robots, and the human beings obviously is the most complicated ones in this coordinate system. There are other drones and also ground robots serves different purpose, and we seeing that we make robots from the third quadrant to first quadrant. That's a gradual improved progress. We can see this graph in another way that probably for robots, there are tremendous numbers of applications we can build. Also, there are a lot of different robotics competitions that emerged in the past decades. We observed a lot of good robotics competitions where people build robots and the competition really help the growth of technologies. We can also put the difficulties of these competitions and the robots involved in them on this coordinate system. We have like BattleBots. It's a competition for entertainment where RC-controlled robots fight with each other fiercely. And we also have very difficult competitions such as DARPA Robot Challenge. And humanoid robots have to work in a nearly unstructured environment to finish a number of complicated tasks. We also have some educational purpose competitions such as RoboCup, where robots play soccer with each other. International Aerial Robotics Competition is famous in drone research community. It's a competition with long history and really helps the development of drones. Well, for these competitions, actually, we want to ask, even if we don't know what robotics applications we want to work on, we can create a robotics competition that roughly covers the range here, in which it means we have a relatively fixed environment, and we are able to let people to build different robots in this competition and use this competition as a benchmark for technologies. That's the purpose of RoboMasters, a competition we make that we hope this competition can sit at the origin of this coordinate system and to help to serve as a benchmark for different robotics technologies. Next, I will use a video to better help me to explain the competition. This video is made by The Verge, a US media.
4、3、2、1。This is the world's biggest, most complex, and completely over-the-top student robotics competition. Over 5 days, students from 200 universities around China compete in front of tens of thousands of fans, while millions more watch online. The whole thing takes place inside this colossal stadium in Shenzhen, an arena that usually hosts the country's biggest rock stars. It's all being funded by Daijing Innovation, Science, and Technology Company. You probably know them as DJI, or at least you know their flagship product, the now iconic Phantom drone. The students are competing not only for cash prizes, but a chance to audition their talents for jobs at DJI. DJI, on the other hand, wants to use this competition to become the most successful robotics company in the world. This is RoboMasters.
This competition is like a battle between robots. So we make some robots to fight against each other.
Each match pits 2 teams of robots against each other. The units maneuver around the field, collecting power-ups and ammunition, ideally without tipping over. The goal is to reach the opposing team's base station. The robots can shoot at each other with cannons, aiming for small pressure-sensitive plates. Enough hits on those plates, and the bot automatically shuts off. The teams can also successfully deplete the enemy base station of all its health and win a sudden death.
So each team will build their own robots, and the robot is mainly consists of 3 systems. So the first one will be the driving system, which has 4 wheels to solve, which enables the car to move around. The second part will be the weapon system, And the last part is actually the judging system provided by the organizer, the competition DJI.
The judging system consists of different components. The sensors to detect coming damage, that's one part. And the sensors for monitoring speed is another part. And we also have another cameras. So the view of the camera will be transmitted back to the operation room, where the operators will only use this first-person view to move their robot.
Every team has 8 robots, including 4 infantry, a hero, a drone, and a base, and also a station that can provide bullets, like a recharging station. So this one is infantry. It has a cannon, and it can shoot bullets. Bullets coming from here, and it can shoot out there.
The small infantry robots can only fire little rubber pellets, while the drone and the hero can use golf balls, doing much more damage with every strike. Golf balls are tough to get, and that's on purpose. In order to access them, teams have to design a mechanical system for collecting and launching them efficiently. Teams that were reliably able to get the golf balls were consistently able to take out the enemy and win the match. Some teams created smaller, faster hero robots, and relied on their drones to collect golf balls, using the aircraft to arm their hero or bomb the enemy base. Others built large hero robots that could scale a central island, climbing over a sea of spikes. Teams developed a wide variety of mechanical solutions, everything from arms and vacuums to wheels on stilts. The mechanical engineering that went into the tournament was always a big hit with the crowd, but the really high-tech stuff was actually happening out of sight in the software.
We forced students to design base robot as fully autonomous. So the base robot can shoot 70mm plastic balls as well, but it has to do it automatically. In this way, we encourage students to involve those high technologies.
At RoboMasters, computer vision was used to enable an autonomous base, allowing it to identify the enemy and return fire without human help. You could see the way the tournament was designed to make stars out of nerdy teenagers. The competition featured live feeds of them operating their robots, documentary films on their preparations, and even an anime series that turned contestants into action heroes. RoboMasters made these students larger than life.
I was pushed to the in front of the spotlight, and I was right in the center. The first time I see the poster, I was also a bit shocked. It's amazing to me. I believe it's amazing to a lot of other people also, especially young children. If they see this kind of thing, it must be like, wow, I'm going to do something like this when I grow up. I really encourage more girls to try it.
Could RoboMasters ever be as popular as a mainstream sport? Will kids one day aspire to be engineers the way they aspire to be rock stars? That remains to be seen. But in the final moments of the competition, when the champions successfully used their hero robot and its golf ball cannon to take down the opposing base station, and the crowd went wild, it sure felt like a roaring success.
That's it. I quickly summarize some of the points in the video. What this competition really be? We designed this place where robots fight with each other. The size of the competition field is roughly the size of a basketball field, and the robots moves in the game field, and the judge system connects the robots into a central server, and the position of those robots will be displayed on the minimap. We develop a localization system to track the position of all these robots and display them for the audience. Then students just sit next to the game field and operate their system. We have Wi-Fi connections and image transmission technologies to transmit back the image view of their robots. So actually, we carefully designed the game elements appeared in this game field to make it a roughly structured environment, but with some uncertainties in it. For example, all the game elements and also the size of the game field is known to the contestants. But those small bullets, golf balls, that teams need to collect brings uncertainty into the competition. The video explains the role of DJI in this competition very well, but we also did more behind the scene. We make some components such as motors and development board, and also a sample robot for students to get a basic idea that how they can get started. Also the judge system. In the video, it also mentioned that the judge system have some sensor to detect pressures change. And we also build our own image transmission link that is nearly identical to those technologies we used on the drones, so that students can get a very good feelings when they operate their systems. Also, we open sourced some technologies that is critical for the competition. For example, the target detection algorithm. This one does not involve deep learning. It's basically just a geometry-based target detection. But this algorithm provides a good example for students who don't know how to design an autonomous system to get familiar with technologies like this and help them to design an autonomous system by themselves. The competition is more than a simple RC controlled game because we're constantly adding new technologies and the game mechanism into the competition. For example, in the coming 2017 competition, we add a mechanism that can be triggered by putting these blocks onto a pole. And the students make robots like this. That is a autonomous system pick up blocks and adjust its position and then place it onto the pole. Since time is limited and this topic's only been proposed several months ago, so students only make large, bulky robots like this. But we expect that in the future, probably students can make mobile manipulators with standard robotics arms to achieve this task. Therefore, when they compete in the competition, they make a mobile manipulator. They're able to use a manipulator to put a box like this. Then outside the competition, they can use the mobile manipulator they created to achieve a real-world task. For example, moving parcels and packages in warehouse or other places. So we extract this exact game element out as the individual technical challenges, which will be hosted on ICRA this June at Singapore. We call it DJI Mobile Manipulation Challenge. We hope to attract graduate students and also professionals who are interested in making manipulation technologies and build robots like this. From the competition like this, we can also verify in the main RoboMasters competition what game strategy would best fit the need of the game. Question?
Pivoting operation is just a grip and force control, or?
Sorry?
Video.
In the previous video?
Yes.
This video is purely...
Just modulate the grip and force?
No, this one has no force detection. It's a completely kinetic measurement because the blocks have labels on it, so we're able to gripping. No force control. This one, I think they hard code the behavior. It's not force closed. Also, this competition can actually be lowered to high school students. In the past winter vacation, we hosted a summer winter camp for high school students in China. We provide a basic sample robot and let high school students who write their own embedded program on this system. And with the help of our engineers and the materials we provided, high school students able to make a completely autonomous system that can move in a certain area and find targets and autonomously track and shoot bullets on that target. Therefore, we think that actually we can dig more from this competition, and we make it an educational programs for high school students. Now, I'd like to share an idea that from a website called Better Explain, where there are two ways to teach students how to learn knowledge. One way is called progressive. For example, in universities, in college, we study calculus, linear algebra, then multivariable calculus, then those materials. Usually, students don't know what is the relationship between these courses. That is the progressive manner. But if we use a course-to-file method to teach knowledge, we can let students first build a simple robot. And in this robot, students may only need to take a few courses to complete the system. And there is more difficult robots, maybe have some target tracking, computer vision-based algorithms in it. Then students need to take more courses to make this robot. Then finally, probably a robot that has force control and can do mobile manipulation requires more mathematical knowledge and engineering courses. And in this way, actually, if we go back to the coordinated system I shown before, actually in this competition, we can let students in a fixed environment to build different types of robots, and all the different robots can find a place in RoboMasters. In this way, we can have a course-to-file training scheme for high school students, college students, and also graduate students. Therefore, after supporting this competition for 2 years, we gradually dig more from it. And for students from high school, we can provide educational programs for them. For people who work on those serious research, we can find some rich research topic in this competition. So there are a lot of possibilities, and we are really excited about it. So finally, I want to also share a vision that we have. Last year, there's a famous AI research called Doom, where a famous FPS game, Doom, was turned into an AI research platform for people to develop deep reinforcement learning algorithms. And actually, it came to me that our RoboMasters provide similar mechanism. We also have image streams that is live and have raw visual input. And we also have programmable control APIs for people to control the movement and also whether to shoot plastic balls from the robot. Therefore, we are looking ways to convert this competition into a deep learning research platform. So I think this is very interesting to work on, and at least we can provide some data sets for the research community to work on. And we also expect to see in the future there is a robots running some deep learning based frameworks that is able to maneuver itself and use deep reinforcement learning to learn to act in this environment. Okay, that's all for my presentation today. Thank you very much.
We have time for some questions.
Please.
Thank you. Excellent work and an excellent talk. I really appreciate it.
Thank you.
I'd like to go back to the subject of the drones. At some point in the future, surely you're going to want to fly at night and in very bad weather.
Yes.
So I'm curious, what do you think are the very difficult problems that you know how to solve?
Mm-hmm.
And what are the problems that are so difficult that now you don't know how to solve them?
Well, there are a number of problems in this criteria. For example, the duration of the flight time. Since we are limited by battery technologies, so we can only achieve 20 minutes or so flight time. That's very difficult to conquer, and we think that it depends on material science and the battery technologies, and we have to move along with those technologies. And the case you mentioned, flying in dark environment, actually we can find some solutions, for example, using infrared cameras to replace normal RGB cameras. That could be solvable, I would say. But we don't see a strong need for this kind of technologies now, because our users use our system to do aerial photography. They won't do it in bad weather or dark environment.
How about bad weather?
Bad weather, I think it's an engineering work. Like we have to continuously improve the waterproof ability, and also make the propellers generate more force when the wind is strong. And these are predictable that we have solutions to do that.
Other questions?
Please.
So for cooperative drones, you mentioned that communication brings in latency and delays. Also, you have so many different heterogeneous processors working together, doing parallel tasks. So do you think the latencies from those processors can be used as, samples to reduce latency in communication, or use that latency in some form for communication latencies? Like, is there some parallel that you can draw from there?
Yeah, there are research called networked sensing and control, where people build models for latencies and try to compensate latencies by various mathematical models. I think there is a good research value for that. And the latencies actually, if we have a really strong communication linkage and we can reduce the latency, but it's inevitable, then we have to devise those mathematical models for latency to compensate them. And I think that will help research in network sensing and control. And I think the results in those research can be useful in this scenario. Did I answer your question?
Sure. My question was that, have you started using these technologies yet? Or?
Well, some.
So I have a question. What do you think about the scaling? Why are these things the way they are, and how much do you think you could grow them? For example, could we just grow them infinitely? Or if there's a natural scale at which these kinds of motors stop working? So you have 6 rotors, you have 8 rotors. We see this company called Evolo that has a thing that's big enough that a person can get into one of these things. Looks like one of these multi-rotor drones. What do you think about the scaling? Is there a natural limitation of this kind of technology, or we could just keep on growing it?
I think actually you can always build strong propellers to generate enough force to lift a heavy drone. So there is no limitation to that in a certain range. And also, I think VJ Kuma have a formula to measure the agility and also feasibilities of the drones. If the drone is large, then its agility would decrease, and at a certain point, it make it infeasible in some applications. For example, the drone is too large that it cannot generate enough forwarding velocities to move forward. So there should be I think there should be a quantitative results connected to that, but I haven't seen anyone done research on that. But I'm sure if the system is too heavy, then it becomes infeasible. And when we choose the size for our system, we gather also data from users, and people say that this certain size is good for aerial photography. Then we work on this size. If it's larger, then we don't see a clear applications for those large drones, then we decide not to move in that direction. So
if I had an application that said we should be able to carry 100 pounds or 100 kilos, is it possible to just scale it up and make just stronger motors, or just scale up the design?
Yes, I think so. But you have to be careful, as I said. If it's large enough, you lose agility, and if you still want it to move really fast, that may not be possible. But you have to do extra engineering works to calculate the resistance or the lifting force that you require. I think from our perspective, everything is market driven. If you have a serious applications, and people will pursue it.
So one of your targets on there is to talk about when you're doing obstacle avoidance, to do omnidirectional obstacle avoidance. I don't think that any of your current products do that right now. Like
Yeah.
So is there like a roadmap on how you're going to accomplish? Is it just more cameras or like?
Yeah, the title of that slide is omnidirectional depth perception. Actually, we can only percept the depths, but it's not a completely omnidirectional sensing. So we have other solutions to do that on our roadmap. I cannot share, but there are a number of ways to do so. Adding more cameras definitely is one solution, and that's on the right track, I would say. Oh, you.
So, throughout the talk, you mentioned that you're trying to make technology more accessible, and it's evident that as far as aerial photography and videography is concerned, you're going along that track. But there's a second really popular application of drones, which is drone racing these days. As DJI, do you have any thoughts of, because that relies a lot more on human operator skill than making it accessible. As a company, do you have any thoughts on whether you want to enter that space, make it more accessible for, say, the hobbyist high schooler, for example?
Well, we do provide a set of propulsion system for racing drones. That's on our website. I'm not selling products, but we do look into that areas. And as I just said to Sanjay, that's our strategy is market driven. I think the decision to enter certain applications made by market. It's not by ourselves.
Do you see the market defining the course of this industry? I mean, there are regulatory laws that you cannot fly drones anywhere and beyond line of sight, at least in the US. Do you see that, I mean, you are developing a lot of technology. Will everything be accepted? I mean, will the acceptance increase to a level that, I mean, will the laws relax to the extent that these technologies will be accepted in the future? I mean, how far can you go?
Well, it's hard to say because we are not lawmakers. But what we're doing is we're trying to make our system more robust and safer. And in this way, that's the best we can do. And we show it to people that our system is safe, and you can lose some regulations on us or other methods. I think as a company, what we can do is make best product, and people will understand and people will accept it. So we don't think more about that.
Do you have plans to open source the code? Because I'd really like to hack it.
You mean like flight control? Or?
Yeah.
Well, the reason we didn't completely open source because there are certain safety critical mechanism. For example, the low-level landing functions, low battery level landing. If the battery percentage is low, we have to force the drone to land. And also, we have a non-fly zone building in all the drones that prevent drones to fly near to airports and also some restricted areas. So those codes are too important to open source. What we are going to do is, as we already have onboard SDK for some of your research, and we're going to open more APIs and also some part of the code that allow researchers to easily develop new research on our products. But there is a certain boundaries and the balance we have to keep. But definitely we're going to open more, especially for research community.
What are your thoughts on like fleet learning or cloud robotics, but for drones? It's like there are examples like with Tesla where they're collecting sensor data back from all of their cars. Do you do the same thing with all the phantoms out there?
Well, it's difficult to collect those data. No, actually, we didn't collect. We don't collect any data from drones unless the drone is being sent back by users. They tell us, okay, your drone has some problem. I need to fix it, and we will extract the flight log from it. But the flight log only record those basic flight control data, no user data. I think we don't see a strong need for collecting data in any application, and that's very expensive to do so. So we currently don't do that. But in terms of research, I think like cognitive robotics or whatever, I think we're going to, as I just mentioned, probably we collaborate with universities and we provide the necessary support to universities and let them to do the research.
So currently, like in a lot of universities, when you're doing drone research, you're almost always forced to use open source systems because you need to be able to access a lot of stuff, right?
Yeah.
Currently, there's only like 2 drone flight control systems that I know of that universities use, PX4 and Autonomy.
Yeah.
Do you plan to compete with them, or like in research realms, like give users more access to your code and
Well, I think we lies in different areas. Like our system, we think that we already have a relatively good controller, and there's from research perspective, like visual navigations and the state estimation, there are many research problems unsolved. But the control of drone flight control itself is a relatively mature area. And I think people will need drones for visual navigation research. They don't need to understand the basic controllers. But if you are working on those basic control problems, probably open source and you can completely get all the principles yourself is better. So I think they are a little bit different.
Okay, I think we're out of time. Good news is that Shuo is going to be at the happy hour, so please continue the discussion there. Thank you for coming. Thank you, Shuo.
Thank you. Thank you.